Hello everyone, let us today introduce one of the most important tools in dealing with discrete linear systems. This is so-called Z-transform. So what is the Z-transform, how we use, we are going to cover in the set of two lectures. So Z or Z transform. Namely, if we just recall the continuous system, the representation x dot a of x plus b of u, y equal c of x, let's assume that the matrix is 0, which is given with a, b, c, 0 set of matrices, and represent continuous states representation. We already learned that Laplace transform was here the tool that we utilized to transfer this system from ordinary differential equation into algebraic expression, where we had y of s is c s I minus 1 b u of s. And by utilizing Laplace transform here, we were able to obtain this input-output system representation, or we were able to obtain this transfer function, which is given as some analytic rational function expression. In the same way, for the difference equation, x plus 1 equal phi of xk plus b, or gamma in this case, I will call this b discrete u of k, y of k, c discrete x of k. We are now interested in what is the tool that will allow us to transform this difference equation into the similar form where we already saw that there is a pulse transfer function given in the form of the backshift operator, and how to relate this difference representation with some transfer function system representation. And to do this, we are going to utilize Z-transform. And in order to simplify what is this tool doing, let us just recall that the Laplace transform is some integral here that is written if we have some function f of t, we apply the Laplace transform of that function f of t, and this is given as f of t exponent minus s of t ds from 0 to infinity. So we see this is expression that defines the Laplace transform. For the Z transform, we introduce so-called Z transformation, which is much simple and more intuitive than this Laplace transform, which is given as an integral expression. Z transform formally just represents mapping from set of sequence into series. What do we mean? What do we mean by this? Is the following. Let's say that I have a sequence of numbers: x0, x1, x2, and so on. So Z transform we'll just map this into the series expression given as x0 plus x1 z minus 1 plus x2 z minus 2 plus and so on. So it's quite simple. Sequence becomes series through the Z transform. And this is the essence, and this is how one can easily understood what happens, because if I have just a sequence of number x, k, and we apply Z transform to this sequence, we are generating now series out of this number by just summing the first term in this sequence with the second term in the sequence, which is x1 multiplies by z minus 1 plus x2 multiplies z minus 2 plus and so on. We go as much as we have here in sequence. If this sequence is infinite, then this is the infinite series. In other words, for the infinite sequences, we have the following: x I z minus I. This is the formal definition of the Z transform. And let us now just check the simple examples, few simple examples of the few common sequence that we can transform by the Z transform into the series, and find out what is the Z transform of this sequence. Let's assume, for example, let's do number 1, pulse function. Pulse function delta k. So let me draw the representation, and here we have that I will use the different color. Here are the sequence in a series generated by this pulse function, because it's 1, 0, 0, 0, and so on. Okay, it's infinite series, but first entry is 1. So if we look, what is the Z transform of delta k, pulse function placed at 1, we have that 1 plus 0 z minus 1 plus 0 z minus 2 plus and so on. So finally we just have a 1. Okay, what if we have a different pulse function, for example delta k minus 3? No problem. We just write 0, 0, 0, 3. Actually, let me put 1 here. 0, 0, here. And how this looks like, this sequence. Looks as follows: 0, 0, 0, 1, 0, 0. So here it's 0, 1, 2, 3, 0, 1, 2, 3. Therefore, Z transform of delta k minus 3 becomes, again, 0 plus 0 z minus 1 plus 0 z minus 2 plus 1 z minus 3 plus zeros plus and so on. So finally we have a z minus 3. In other words, we see how the Z transform of the simple pulse function transforms every pulse function into appropriate expression, and z in this case is a complex variable. Finally, let us consider the last case in this short lecture. This is the case of the function that is unit step function. So we have a unit step function. Unit step function. UK given as 1, 1, 1, and so on. So all ones. How we put this in the picture? It's like this. And here we have a 1, then 1, then 1, then 1, then 1, and so on. And if we apply Z transform in this case, U of k, we will have that 1 plus z minus 1 plus z minus 2 plus and so on. It leads, surprisingly, that if we are just summing all of this with a z being z minus 1, z minus 2 plus z minus 3, this finally becomes z minus 1. How is this possible that this infinite series becomes some finite expression? This is going to be explained in the next lecture, but behind of this is a just notion of geometric series.